So, hello everyone, my name is Rémi Castera. So today I'm going to present you a paper called Statistical Discrimination in Stable Matching, which is a joint work with my two PhD advisors, Loiseau and Bary Pradelski. So here is an outline of the presentation. So today I'm going to talk to you about college admission. There has been a lot of criticism regarding college admission procedures these last years, and especially in France. And maybe, I don't know, a lot of you probably don't understand French, but believe me, this is bad. So yeah, we have a lot of criticism regarding that, and a lot of people think that the outcome of these college admission procedures are unfair. So obviously, we can think that if it is unfair, it's because the preferences of the colleges are unfair. But the question I'm going to look into today is whether this is the only source of unfairness. So I'm going to talk to you about statistical discrimination, which was defined in the early 70s. So what is statistical discrimination? Is the fact that you have several groups inside the population who have different outcome distributions in a process, which comes from imperfect information of the decision maker. So this is not discrimination that arises because the decision maker is biased, but because of distributional features of the population. So literature about statistical discrimination has been quite limited to selection problems, which is when you have one decision maker, for instance, one employer trying to hire some people. And so the insight we have from this literature is that statistical discrimination can occur because of bias, obviously, but also because of different noise variances. If you have a decision maker that is not biased, so you have two groups in the population, and the score distribution of both groups have the same average, but the variance is different, then you will have different outcomes for both groups, and one of the groups will be overrepresented. So the question we address today is whether we can have these kind of things in matching programs. And what I will show you is that we have a new feature in matching programs that didn't exist in selection programs, which is the correlation between the estimates of each candidate quality by decision makers. So here is a small example. Imagine you have two colleges, A and B, who have different criteria. So college A prefers students who are good in math, and college B prefers students who are good in physics. The applicants come from two high schools. One high school where physics is taught in a very theoretical way. So students who are good in math are also good in physics and vice versa. But you have another high school where physics is taught more through experiments. So the grade of the same student in math and physics are more independent. So what you end up with are two distributions that look like this. You see that on the left you have high school 1, where the grades are very much correlated, and high school 2 on the right, where it's not very correlated. And our question is, do the students of one of these two high schools are advantaged compared to the other because of this feature of the distribution? So here is our model. We consider a continuum of students. So we use a measure called eta. So the total mass of students is 1. The student set is divided into two groups that we will call G1 and G2, so they have respective masses of gamma and 1 minus gamma. We have two colleges, as I said before, with respective capacities alpha A and alpha B, and we have this one assumption that alpha A plus alpha B is lower than 1, which means that some students will get rejected from everywhere. There is not enough room for all students to get admitted to college. And don't focus too much on this assumption, because when you don't have this assumption, the problem is just totally trivial. That's why I put it here. And so inside group G1, we have some students who prefer college A, and we call this proportion beta 1. The rest of group G1 prefer courage B, obviously, and you have the same in group G2. Now, each college needs to produce a ranking of students in order to know which one they admit and which one they don't admit. So to do that, they will just give a grade to each applicant. What we're focusing on is the role of correlation between the grades that are given to the same student but by both colleges. So we suppose that we have these grade distributions. So if we take a student, S, she has a vector of grades, WSA, WSB, and that is a normal bivariate vector with this covariance matrix. So we suppose that the variances are the same, but we have here this factor, which is the correlation between the grades that she gets at college A or college B. So we can imagine that there are very different possible correlations, and you see on these three plots that each time the marginals are the same. All right. So the grade of students from group G1 and group G2, from the perspective of each college, the distributions are the same because the marginals are the same. The only thing that differs between two groups is the correlation, which is something that is not that is hidden from colleges, right? From colleges' perspective, they are not discriminating. They give the same distribution to everyone. So what we're focusing on is stable matchings, which is a very classical thing in matching theory. So to be very quick, we say that a matching, which is an allocation of each student to a college or to no college. So we say that this allocation is stable if for each student who hasn't been admitted to a favorite college, then everyone who has been admitted to a favorite college had a better rank than her. So this is a very basic notion of fairness. If you're rejected from somewhere, it means that everyone who has been admitted was better than you. And so what this tells us is that the matching is looking like this, what we can see in the figure. So if I take students who prefer college A, the ones who are admitted are in the green zone. So they are all the students who have a high enough grade at college A. But for the one who didn't have a grade high enough at A, they can still be admitted at college B as their second choice if they have a high enough grade at B. And for students who prefer college B, it's the opposite. Now, keep this figure in mind because now I'm going to define something very related. So let's take two numbers, PA and PB, which we call cutoffs. And so they represent the grade of the worst admitted student at each college. So PA is the grade of the student that was last admitted at college A. PB is the worst student admitted at college B. And now we can use this to define who is admitted where. Because so we define these demand quantities. So the demand at college A is the amount of students who prefer college A and who have a grade higher than the cutoff, but also the students who would have preferred college B. However, they didn't pass the cutoff at B, but they pass it at A. So what they demand is college A. And now what we do with these quantities is just a supply and demand argument. We say that the cutoffs PA and PB are market clearing if the demand at each college is equal to the capacity of this college. Now, to know what the matching will look like, we just need to find the market clearing cutoffs. And this is taught to us by a very nice result by Azevedo and Reshno, who say that when you have a continuum of students, the stable matching is unique, and it is given by the unique pair of market clearing cutoffs. So here, we don't have to run deferred acceptance or such kind of algorithm. We just need to solve this equation. Now, I'm going to focus about matching outcomes. What I'm looking into is how many students from group 1 will get their first choice or second choice or remain unmatched, and same for group G2. So that with these quantities, I can compare if one group is advantaged compared to the other. So for instance, if I'm looking at the probability of a student from group G1 who prefers storage A to get their first choice, then it's just the probability that they have a grade higher than the cutoff. And it's the same for storage B and for group G2. So these are the quantities for people having their first choice. And I can do the same for people getting their second choice, right? So the probability of getting your second choice when you're in group G1 and you prefer storage A is the probability to have a grade that is lower than the cutoff at A, but higher than the cutoff at B. So you would prefer A, but you will get admitted to B. And obviously, the dependence on the group is on the probability distribution, because they are not the same for both groups. And for students remaining unmatched, is the same. So the probability of staying unmatched is the probability of having a grade that is lower than the cutoff at both storages. So now, if you want to compute the stable matching, which is unique, I remember you, we just have to solve the Marquet-Turing equation, which is this one. It's a bit ugly, but I mean, if you take, for instance, the first term, it's the probability of getting your first choice when you prefer A and you're in group G1, multiplied by the mass of students in group G1 and the proportion of students in G1 who prefer A. So, I mean, it's not that complicated, just a bit ugly. And the sad thing is that this equation has no analytic solution apart from very specific cases. So we cannot directly compute the cutoffs and then the probability of having your first choice, etc. However, we can still use it to derive some qualitative results, and that's what I'm going to do afterward. So the first question that we can ask is one group advantaged compared to the other, which was the first question that we mentioned in this presentation, and here is the answer. The probability of getting your first choice is the same for every student. I mean, it doesn't depend on whether you belong to group 1 or group 2. However, the probability of getting your second choice and the probability of staying unmatched, which is getting rejected from everywhere, it depends on the group. And so you have, if you belong to the group that has the highest correlation, then you have a higher probability of being rejected from everywhere and a lower probability of getting your second choice. So what we can conclude is that you have a worse outcome when you belong to the high correlation group, which is the exact definition of statistical discrimination. So that is the first answer. So here is a quick illustration of why this happens. So if you look at these two plots represent the two groups. So you have one with low correlation and on the right high correlation. And if you look at the amount of students that are on the right of the cutoff PA, and then this quantity is the same in both plots. Maybe it's not obvious, but it's the same. And so that's why the probability of getting your first choice when you prefer storage A is the same for both groups. And similarly, the probability of being above the cutoff for storage B is the same for both groups. The difference is that if you look at the right plot and the amount of students in the lower left quadrant, there are more in the right plot than in the left plot. And what does this tell us is that the probability of being unmatched is higher for the high correlation group. And therefore, the probability of getting your second choice is lower. Now we can ask ourselves another question, which is what happens if we manage to change the correlation level of one group, or maybe of both groups? And here is the answer. So if you increase the correlation level for one group, you increase the probability of getting their first choice for every student, even in the group whose correlation level hasn't changed. On the other hand, if you do that, if you increase the correlation level for one group, you will decrease the probability of getting their second choice for this group. And you will increase the probability of staying unmatched. So let me recap this. If your on-group correlation level increases, you have a higher chance of getting your first choice, but also a higher chance of being rejected from everywhere. On the other hand, if you're not part of the group whose correlation is increasing, then you will have a higher chance of getting your first choice, but a lower chance of being rejected. So it's all good for you. You don't want to be in the group whose correlation is increasing. You want to be in the one which doesn't change. And here is an insight as to why this happens. So if you imagine that you have one group and that you increase its correlation level, then the amount of points in the lower left quadrant will increase, which means that you will have more students that are unmatched. But this cannot happen because the number of students that are unmatched is constant. It's 1 minus the capacities, right? So it cannot increase. So what happens is that the cutoffs will have to decrease. And when you decrease the cutoff, you increase the probability of getting your first choice. But there is also this more complex effect on the probability of getting your second choice or remaining unmatched. So I don't think that I have the time for another motivating example. So I'm going to switch to the conclusion. What we show in this presentation is that differential correlation has no effect on good students because the probability of getting your first choice is the same for everyone. However, if you're an intermediate student and you're borderline of getting rejected from everywhere or getting your second choice, then you're better off in the low correlation group. If you increase the correlation level for one group, it will benefit good students from both groups because if you are borderline of getting your first choice, then it will be good for you even if you're in the wrong group. But if you are an intermediate student, then an increase of your own correlation level is going to hurt you. And an increase in the correlation level of the other group is going to benefit you. On a more high level, what we see is that the admission process is not unfair in itself in most cases, and it doesn't need to encode discrimination itself, and colleges don't have to be unfair by themselves to have an unfair outcome, right? So you can have statistical discrimination even when colleges have the same grade distribution for everyone. So correlation is really something you have to take into account when you're studying discrimination in matching programs. And so in this presentation and in this paper, we isolated the effect of correlation, and that leads us to have a better understanding of statistical discrimination in a matching context. And our results can already be applied to several different settings, and that unfortunately I didn't have the time to present to you. But they also may be used to study more complex models where you have, for instance, different variances across groups, maybe more colleges or students' preferences that are correlated to their grades and things like that. And yeah, so this is the end of my presentation. Thanks for your attention.
We have time for one question. So the first one I saw, unfortunately, is going to be you, sir.
So I had a question about the first result you gave, that the probability of getting your first choice is the same. So I wonder if you could go to the picture. So I guess what I'm saying is, it looks, and I know this is, so I guess I'm wondering how sensitive your result is. So of course, the more correlated group has more people in the top right-hand box.
Yes.
But fewer people in the side boxes.
Yeah, exactly.
So somehow this is exactly offsetting, where the number of people in the longer boxes, they also get their first choice sometimes. So I wonder how sensitive is that to distributional assumptions?
It is, anytime you have normal distribution, you have this result. And actually, why I use normal distribution is because I don't know any other way to change the correlation without changing the marginals.
I see.
And so I don't know if you could do this with other distributions that are not normal. But if you have a normal distribution, you always have this result.
Thank you.
see. Do we have any questions online for our speaker?